differentiation of vectors. So here we define first scalar potentials which are denoted as f of xyz or phi of xyz and so on, and then vector potentials denoted as f cap or f bar is equal to f1i plus f2j plus f3k. Obviously, because these are all field vectors, this is a field vector, f1, f2 and f3 are functions of x, y and z in the Cartesian system. One can easily visualize that as one moves out of Cartesian to spherical and cylindrical polar coordinates, those respective coordinates will be seen in f1, f2 and f3. But in the present context, we will stick to the Cartesian coordinate system. Now, once these two types of potentials have been defined, in vector differentiation, the first concept is the concept of gradient of a scalar potential. Now, mind you, gradients are defined only for scalar potentials and not for vector potentials. So, how do we define? Gradient of phi is defined as del phi, where del is the vector differential operator. So, to that operator, if you attach phi, you get dou phi by dou x I plus dou phi by dou y j plus dou phi by dou z k. So, this output is always a vector. So, what does this mean? So, the interpretation is, if phi is equal to 0 is a geometrical surface let us say we have a geometrical surface and P is any point on the surface, then the surface normal, this is the surface normal, which is nothing but the gradient vector. So, gradient vector represents the surface normal to a given surface. Obviously, if it is a bending surface, the surface normals will be pointing in different directions and of varying lengths. But once the surface is a flat plane, then all the surface normals become mutually parallel and also of the same length. Alright. So, now we would like to see how the gradient is very useful in certain investigations in field theory. We are interested in two applications of the gradient. One is angle between surface normals in which we have, say, a surface say phi, and we have 2 points P and Q on the surface, and we are interested to find out the angle between the surface normals at these 2 points. Let us say this is the surface normal at P and this is the surface normal at Q. So, this is del phi evaluated at P and this is del phi evaluated at Q. All we need to do is to measure the angle between these two vectors. Of course, extensions may be required, and once you extend, that angle can be computed. So, we can get theta is equal to cos inverse del phi at P dot del phi at Q by the magnitude of del phi at P into the magnitude of del phi at Q. So, obviously, you will get an angle somewhere between 0 to 180, but acute angles you can just take the modulus and then compute that. Now, we have already discussed what are meant by orthogonal vectors. Similarly, here if theta becomes 90 degrees, then these two normals become orthogonal to each other, and the condition for that will be the numerator is equal to 0. The same thing can be used whenever we have two surfaces intersecting at a common point and we are interested to find the angle between them. So, the angle between two surfaces at a point almost follows the same formula, and let us put, however, if phi and psi are two surfaces intersecting orthogonally at a common point P, del phi dot del psi is equal to 0. So, this is one of the applications of the gradient. Of course, the gradient vector is also very important in the context of function optimization, which we briefly discussed in the partial differentiation. So, if you take the gradient vector and equate it to 0, you get critical points which can then be used to analyze a function for maximum or minimum values. That is where the context of Hessian matrix comes into picture. So, the gradient vector is extremely important in the present context for angle determination between surfaces. At the optimization level, it is used to find out the maximum or minimum of functions. So, let us go to the next application of the gradient. In the next application, we will study directional derivatives. Directional derivative of phi along A. Phi is a scalar function or a scalar potential, and A is a given direction. Now, the idea behind this application is we have some surface phi and we are given a certain direction A. This is a fixed direction. Let us say we have a point on phi called P, which will be specified by its coordinates, at which we can draw the surface normal del phi. So, we have three pieces of information. One is the surface and its equation, the point P along with its coordinates, and a fixed vector A. So, now if you take the orthogonal projection of del phi on A, this is nothing but the directional derivative. So, how do you compute the directional derivative? Directional derivative is equal to del phi dot A by the magnitude of A, or del phi dot A cap. So, that is how the projection of vectors concept is very important in study of directional derivatives. Now you can imagine a situation where we are trying to maximize the directional derivative. If this directional derivative has to be maximized, then this vector del phi must be parallel to the vector A. So, for maximum directional derivative, we align vector A along del phi. So, when these two become parallel, then directional derivative maximum value will be equal to the magnitude of del phi itself. So, we have very important information here. This is generally the formula to calculate directional derivative, and this is a specific case where we are maximizing the directional derivative. After this, let us go to the concept of divergence. So, the divergence of a vector field. So, we do not define divergence of a scalar field, scalar potential. We define divergence of a vector field or a vector potential. So, if you let f is equal to f1i plus f2j plus f3k to be a field, divergence of f is defined as del dot f. So, take the vector differential operator and take dot product with f. Because del contains ijk's, f also contains ijk's, and the dot product should definitely give us a scalar. So, the working formula would be dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. Obviously, this is a scalar quantity and there are three possibilities. One possibility is divergence f is equal to 0. So, if you imagine a field in which the flow is like this, that is, whatever enters the field also leaves it, then we say the divergence is 0. Then f is called, in this case, a solenoidal field. The second case, when you have del dot f greater than 0, in which case we have the field vectors leaving from that particular point. And the third case, when we have del dot f less than 0, in which case we have the field elements entering. So, these are the three possibilities where we have interpretations for the divergence. Of course, the divergence calculation is extremely important when you come to vector integration, when you have that very famous theorem due to Gauss. We will come to that issue after we define curl. The curl of the vector field is del cross f is equal to the determinant ijk dou by dou x, dou by dou y, dou by dou z, f1, f2, f3. So, this produces a field as an output. Now, here there are two possibilities. If the curl is 0, f is called irrotational. In one context irrotational, in some other context it is called conservative. We will discuss the conservative field aspect when we come to vector integration. Now there is an interesting result in this case where the curl becomes 0. What does it say? It says if f is irrotational, which means we have a field in which the field elements do not have any spin effect. There is no spin effect. Whereas in the rotational case, you will find the vectors are curling around a point. Okay? So when f is irrotational, we can find a scalar potential such that del phi is equal to f itself. So this can be determined. I will not be able to say uniquely, but under set of conditions we can find phi uniquely. But as a general rule, del phi is equal to f can be always used to find the scalar potential. And when we come to the study of conservative fields in vector integration, we can exploit this scalar potential to find out the work done by the field if it is conservative. We will come to the issue later on. Now, these things which I have mentioned in the last 2-3 slides are going to be very important in framing of questions. There can be challenging questions, there can be fundamental questions, but at the base one must be very good in partial differentiation, expansion of determinants, and of course in this last case where we have to find the scalar potential, we must be good at partial integration also, which we will actually see while working on problems. So now we will begin an exercise on these 3 concepts, and we will hopefully get good insight into how to handle problems given a thorough knowledge of all the fundamentals.